You're calculating the kinetic energy of each one of these things. Regina, grab your notes out. Answers. 2,268.75 joules, 1,350 joules, 200,000 joules, 40 joules, 2,560 joules, and the swing is the more important piece to that. Comments, questions, concerns. Is there anything anyone would like me to go over? Yes, I see that hand, Evelyn. Because if you look at the formula, 1/2 the kinetic energy, EK, equals 1/2 mv squared. Let's see what the effects are of changing. So like if I pick some numbers at random, I'll pick some nice easy numbers. If I make the mass 1 and the velocity 1, it's going to be 1/2 times 1 times 1, which is 1. No, which is 1/2. If I change this to 2 and leave that as 1, it's going to be 1/2 times 2 times 1 squared, which is going to be 1. If instead I go 1/2 times 1, I leave the mass the same, and I double the velocity, I'm going to have 2 squared, which is 4, times 1, which is 4, times 1/2 is 2. I changed the mass and the velocity the same way. The velocity had the bigger effect. So the speed of your swing, assuming everyone's using the same bat, if you can maximize your swing speed, you'll have a better chance of hitting the ball harder than you would if you just went and got a heavier bat. Yes, Kaylee. Can I go over number 1? You betcha. Kinetic energy is equal to 1/2 mv squared. Mass is 1.5. Velocity is 55. So it's going to be 1/2 times 1.5 times 55 squared. And if I punch that into my calculator, I should zoom this in so it's not so hard to see. 55 squared times 1.5 times 0.5 equals that. Did you did this exactly the same way and got a different number? Yeah, that's okay. This is how I typed it in on mine. You could type it like you go in order 0.5 times 1.5, or you can use the brackets as it's written. 1/2 0.5 bracket 1.5 close bracket open bracket 55 close bracket squared. Oops. Okay, any other comments, questions, concerns? Cool. So we did review some math before. How do we feel about that? Should I review some more math or should we just go for it? Full send? Okay, we're going to full send. If anyone would like me to review the math, I can review it with you individually after people are working on stuff. Here we go, full send. So yesterday, I introduced you guys to the concepts behind kinetic energy. We formalized how it works. I mean, we talked about it. We said you guys all agreed mass and velocity are the things that are going to be involved when a moving object has a bunch of energy. And then we calculated it. I gave you the formula yesterday, and we said, okay, I said kinetic energy is 1/2 mv squared. Take my word for it. You'll figure it out later. If you take some calculus, you'll see where it comes from. If you don't take some calculus, you'll never know. And we just solved for a bunch of EKs. Today, what we're going to do is we're going to solve for other pieces of the equation. So something like, well, the first one we've already done. Let's review, shall we? And there's 2 ways to write this formula out now. I was messing with some students. I didn't realize it was messing with some students yesterday, but it's important to recognize that 1/2, the fraction, can be written as 0.5, the decimal. That was confounding some students yesterday. If that's causing you grief, I can explain that if you'd like, or we can just go with it. Something you need to know. So let's solve some of these things. Example, find the kinetic energy. This is exactly what we did yesterday. EK, find the kinetic energy. So let's write out the formula. EK equals 1/2 mv squared. Okay, what do we know? We know the mass of the bowling ball is 5 kilograms, and the velocity of the ball is 10 meters per second. I can just plug this in and away we go. That's going to equal 1/2 times the mass, which is 5, times the velocity, which was 10, and I have to square the velocity. So you can use a calculator for this. You do not have to use a calculator for this, because 10 squared is 100, and 100 times 5 is 500, and then half of 500 is 250. And the units on energy are always joules. So for full marks, I need to see all those pieces there. But what if we make it more interesting? This is likely the way the question will be worded. Find the velocity of a 5 kilogram bowling ball. No, let's not do it that way. That's lame. Let's make it a heavier bowling ball, because why not? Let's make this a 5 pounds, or 5 kilograms is 4, 6. Okay, so that's an 11-pound bowling ball. Let's make it an 8-pound bowling ball. Let's change the question. Let's say we have a 3.6 kilogram bowling ball, and usually the way it will be worded will be something like this. The first one was find the kinetic energy of a 5 kilogram bowling ball moving at 10 meters per second. Question 2, or part B to the same thing, will be find the velocity of the 3.6 kilogram bowling ball that is traveling with the same kinetic energy as the 5 kg ball was. So you're at the bowling alley. We don't have a 10-pin bowling alley in Abbotsford, I don't think, anymore. They closed it down, made a mattress store. Where? Galaxy's 5-pin, not 10-pin. We used to have Dogwood Bowling, but then they closed it for some reason. Apparently bowling's not as popular. And so you can get, so a 5 kilogram ball is an 11-pound ball. This is an 8-pound ball, so the balls are getting lighter. We want to find how fast a smaller ball would go if it had the same kinetic energy as the previous ball had. So we want to find the velocity in this case, but it's still going to use the same formula. We're still going to have EK equals 1/2 mass times velocity squared, except now we know something different. We know the mass is 3.6 kilograms, and we know the kinetic energy, EK, is the same as the previous one. Well, the previous one was 250. So these are the two things we know, and so this is what's going to get substituted into this equation. So the 250 now is going to go on the left-hand side where the EK was. So 250 is going to equal 1/2 times 3.6 times V squared. And now we're going to go and solve for V. We okay? Well, what? Yes. Surprise. The district's making some interesting decisions. And we don't get to eat. I mean, the reason it's closing is because there's no students for the program. It's the other way. Like, they say there's no students for the program, so they're cutting the program. But how much? Back to this. So let's solve this thing now for V. Yes, next year there will be no cafeteria, but that is not today's problem. Today's problem is, what's the velocity of the bowling ball? So now we want to solve this thing for V squared. What do we do first? To make our life easier, well, there's two ways you could do this. We're multiplying by a bunch of things here, right? We've got V squared times 3.6 times 1/2. And a way to deal with this is just to divide these all down. Or I could make this right-hand side a little simpler. I could take the half and the 3.6 and I could multiply them together. What's half of 3.6 without a calculator? Here's a trick for you. What's half of 36? You square rooted it. Half of 36 is 18. So instead of 36, it's 3.6, so it's going to be 1.8. You could use a calculator if you wanted. So we can take this and we can make it a little bit simpler. We can say, okay, well, this is just 250 equals 1.8 v squared. And I still need to solve this thing now for v squared. It's important to recognize, Regina, put your phone away, that you're multiplying in between here. So to get v squared by itself, the first thing we do is we need to divide by 1.8. We're doing the opposite of BEDMAS. That's going to cancel this, and we're going to be left with, where should I go? Let's go this way. V squared is going to equal, well, whatever 250 divided by 1.8 is. That's going to be 138.9. I rounded it. And now I want to find V. How do I find V? If I have V squared. Coe, square root both sides. So V is going to equal the square root of 138 point that. And I'm going to get 11.8 meters per second. So, let's look at what we've done here. We took a smaller ball and we threw it with the same amount of kinetic energy. The velocity should go up. If the kinetic energy stays the same and the mass goes down, this needs to go up to compensate. And we found that if you took a lighter ball and threw it just as hard, it would go faster, which shouldn't be an earth-shattering result. That's common sense. Questions, comments, concerns about what we've done here? As opposed to what? If you told me 11.8 was 11, yeah, I'd take off marks for that. Because you didn't round it, yes, if you did not round that properly, I would take off marks for that, absolutely. You need to make sure you're using your rounding skills that you've been working on since elementary school to round these things properly. Don't just cut off the numbers. And I say that, and you chuckle as grade 10s. That's marks I'm still taking off with my Physics 11 students. They'll just chop numbers off and call it good. Like, no. Those numbers mattered, especially when we're dealing with scientific notation, and it's not 11.8. It's 11.8 times 10 to the 2, which is 1180. Is that right? Yeah, 1180. And they'll just call that 1100 as opposed to 1200. Like, when the numbers get bigger and you're dealing with things like scientific notation, rounding like that can change the number massively. So yeah, round it properly. Okay, we have another one. We have a car. A car is traveling at 10 meters per second and it has 25,000 joules of energy. What's the mass of the car? Or, you know what? No, I won't do that. We'll leave this question the way it is. I'm not going to change it for you. So, it's still important to recognize that you've got a car that's moving with energy. A moving car has kinetic energy, so this is a kinetic energy kind of question. So we're going to use the EK equals 1/2 mv squared equation and write down what you know. We know the car is traveling at 10 meters per second. That's a velocity. We know the thing has 25,000 joules of energy. That's kinetic energy. And this is what we're going to shove into our equation. And we're going to solve this thing now, not for the velocity or the kinetic energy, but now for the mass. So 25,000 is going to equal 0.5, let's bring in the decimal this time, times the mass times 10 squared. Now, recall from yesterday that 10 squared is, that 10 is 36 kilometers per hour. 10 meters per second, 36 kilometers per hour. So this is just, you're speeding through a school zone. What's the mass of the car with 25,000 joules of kinetic energy? speeding through a school zone. How do we solve this thing? Yes, but what's the first thing we should do? Square the 10. Yes. So we're going to get 25,000 equals 0.5 times m. Now, 10 squared is 100. We're going to evaluate that. Now we're going to clean up the right-hand side again. How can we clean up the right-hand side? Find half of 100. What is half times 100? 50. So this is going to become 25,000 equals 50 times m. I squared this first, got this. I multiplied these two things together and got 50. And now the last step is to solve this thing for m. To get m by itself, the last step is divide it by 50. Good. And we're going to get, I think I just heard it, the mass of the car should be 500 kilograms. To put that into perspective for you, because I like doing that, I like giving you perspective. What does it mean for a car to have a mass of 500 kilograms? An example of such a car would be, oh boy, okay, so this is smaller than a smart car. Oh boy, this is a tiny little thing. Sahej, good morning. Okay, so a 500 kilogram car is smaller than one of those little smart cars. It's a very small car. A lot of energy though. Okay, I would like you to do number 4 on your mark, set, go. On your own. You can do it. I believe in you. Yeah, man. Did you figure it out? Okay. Okay, what do we got? What is the velocity of this elevator? We found it to be 4. Okay. Does anyone want to see how we got 4? Comments, questions, concerns? Would anyone like to see it? Let's do it real fast. Here we go. If you have the velocity and the energy, we want the velocity. We have the mass, 500 kilograms, and we've got the energy. If it's moving, that energy is kinetic. It's 4,000 joules. And this is the formula we're using, 1/2 mv squared. So let's plug it in. 4,000 equals 1/2 times 500 times v squared. We wanted, Evelyn, the first thing I would do is I would just multiply these two things together, clean them up. It's going to be 4,000 is going to equal 1/2 of 500 is 250. And then I'm going to divide this by 250, divide this by 250. Boom, boom, boom. 4,000 divided by 250 is going to be 16. So 16 equals v squared, square root, we get v equals 4. And then we need to toss units on that. Velocities are always measured in meters per second. Cool, nice and easy, relatively straightforward. Let's make it more interesting. I want you to flip to this page. I'm going to flip back once again. When we talked, we said that if we're talking about gravitational potential energy, the things that are going to impact the gravitational potential energy are the height from which an object gets dropped, the mass of the object getting dropped, and what the gravity is where you are. And I told you that Earth's average gravity was 9.81 meters per second squared. So, let's do the same thing now, except we're going to take a look at Sorry, my bad. Gravitational potential energy instead. Here we go. We said that those were the three important variables, so here they are. Gravitational potential energy, so this is often called PEG or EPG. Energy, potential, gravitational, it's backwards. You'll see this both ways. Is going to be equal to the mass times the gravity times the height of the object above whatever you're going to call 0. This height here is above 0, and heights are always measured in meters. In science, we always measure in meters. G on Earth, fill it in here again, is going to be equal to 9.81 meters per second squared, because that little g is actually an acceleration. It's the acceleration due to gravity. And mass, again, as always, is going to be measured in kilograms. So let's find a bunch of potential energies here. There is a bell at the top of a tower that is 50 meters high. The bell weighs 10 kilograms. What is the potential energy of this 10-kilogram bell 50 meters above the ground? Or how much would it suck if this bell fell on you? That's effectively what we're answering here. So let's take a look at this. It's important. I'm not going to tell you find the kinetic energy. I'm just going to say what is the energy. You need to recognize now which of the equations that you've been given are the ones that is important for you to use. This thing is not moving. So kinetic energy is not the topic we're going to look at here. We're going to look at gravitational potential energy because it's at a height and it has the mass, and presumably this is on Earth. So I want to find the, I'm going to call it PEG. Potential energy gravitational is going to equal mgh. Well, just like before, we know h is, we know mass is, and we know g is 9.81 meters per second squared. The mass of the bell is 10 kilograms, and the height of the object is 50 meters. Again, to put that into perspective for you, 50 meters, where's my calculator? 50 divided by, let's go there. That's like 17 stories. It's on the 17th floor of a building, or bell tower or whatever. We're going to take these values, we're going to plug them in, just like we substituted before. Mass is 10, G is 9.81, H is 50. We're just going to multiply those three values together, and you're going to get that the potential energy is what? We're going to multiply those three together, and you're going to find that the potential energy is what? Sorry? Because I don't like EG or PEG. I don't like this. I like this. The first one I gave you with the P out front. Potential energy, and then what kind of potential energy? It's gravitational. What's the value? 4,900 and what? You betcha. Which means, if that bell decided to fall, whoever is beneath the bell is in for a world of hurt. Because all of that gravitational potential energy is going to get transferred to whoever is underneath the bell when it impacts the ground. Yes, Evelyn. Yeah. I mean, is the giant stuffy 10 kilograms? I didn't say this would kill someone. I just said they're in for a world of hurt. Yeah, if you dropped a 22-pound object, even if it is just a big stuffed animal, if you dropped a 22-pound object or a 10-kilogram object onto someone from 50 meters, half a football field up in the sky, yeah, that would suck. That would suck a great deal. It probably wouldn't kill them, but they wouldn't be happy with you. Yeah. Okay. We're going to skip 2. Actually, these are all the same. We're not going to skip 2. We'll just do it. It's the same kind of question. We're not going to do all of these because all of these, it's exactly the same. Find the potential energy. What is the potential energy? What is the potential energy? What is the potential energy? It's the same calculation 4 times. I will do one of these. Evelyn, because you're full of questions this morning, you get to pick. Which one of these 3 would you like to see? The mass of the car that is lifted, the roller coaster at the top of a 70-meter hill, or the potential energy of a 3-kilogram ball on the ground? Number 2, here we go. We have a 10-kilogram mass lifted to a height of 2 meters. What is the potential energy? Okay, well, we know. It says what is. And so that's going to give us the clue of what the formula is that we're going to use to solve for whatever. PE is going to equal mgh. Do we know the mass? Yeah, we do. It's 10. Do we know the height? Yeah, we do. It's 2. Do I know the words gravity? Yeah, 9.81. Take those values, plug them in. 10 times 9.81 times 2. What is the gravitational potential energy of a 10-kilogram mass lifted to a height of 2 meters? So it's above my head. Like 2 meters, 2-meter sticks. Like that's not that high. What is the... Now we're just punching that through a calculator. 10 times 9.81 times 2. You betcha. I want you guys to do 3 and 4, if you haven't already. Some of you I know are done 3 and 4 already. Take a look at 3 and 4. Tell me what you get. What is the energy of the roller coaster? What's the energy of the ball on the ground? Okay, what do we got? They're supposed to be. What is the potential energy of the roller coaster? Who's got a number for me? Yes, Brooke. 68,670. That's what I got. Excellent. And number 4, nice and easy. What is the potential energy of a ball on the ground? You betcha. Because for to have gravitational potential energy, you have to be above the surface. If you are on the surface, you are not above the surface. You have no gravitational potential energy. You're not going to be able to get anybody underneath it to hurt them with it if it's on the ground. No. No. An ant is not going to go under the ball that's already on the ground. You'd have to dig down, and now you're at negative height. And so you'd have negative potential energy. How does that even make sense? But it's a thing. Okay, flip the page. Last set of examples, and then you're going to have a bunch of time to do some word problems. It's going to be great. There we go. Because that's all this is. Physics is just very specific word problems that you could probably have done in grade 8. That's okay. Here we go. The law of conservation of energy. Recall this law. The law of conservation of energy says that energy is neither created nor destroyed, but it is transformed from one form to another or transferred from one object to another. We've said it before, we'll say it again. Now, though, we've got some specific things to talk about here. The law of conservation of energy says that the total energy at the beginning must equal the total energy at the end for every single one of these problems. And so what that means is, we can write it out like this. The initial energy, I'll call it EI, has to equal the final energy, EF. And what kinds of energy have we looked at already that an object could have? Could you contrive a scenario where an object started with kinetic energy? The object starts moving. Is that reasonable? At the beginning of a problem, could you give an object kinetic energy? This is not a trick question. The question could start with something like, the roller coaster is moving at 5 meters per second. Right? Like, I could use those words. So yeah, of course, we could have an initial amount of kinetic energy. Could we have an initial amount of potential energy? Could I say that the roller coaster is moving at 5 meters per second, 6 meters above the ground? Those words make sense. So now you've got a scenario where you have a moving object at a height. This is the premise behind what Mahip was doing yesterday when he was skipping class. Mahip went to Playland, rode a bunch of roller coasters. Mahip had a potential energy of, Mahip, let's talk about Mahip. Mahip's moving at 5 meters per second, 7 meters above the ground. The roller coaster goes down the hill. So as the object goes down the hill, what's happening to it? The kinetic energy is going up, and the potential energy is going down, because he's traveling towards the ground, and the rate of speed is going up. So there's going to be kinetic energy possibly at the beginning, and there's going to be potential energy possibly at the beginning. And at the end, there could be kinetic energy, more of it, and there could be potential energy, more of it. And so now we've got this big fancy equation. It started with energy initial has to equal energy final. That is the law of conservation of energy. And now we've got, well, I've got kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. All of the kinds of energy that you could have on both sides. And then we could bring in springs into this. We could say you have a cheeseburger moving at 10 meters per second. I launch a cheeseburger at Jedediah from on top of the school. The cheeseburger has a certain amount of chemical potential energy. If I hit Jedediah with the cheeseburger and he eats it as it's flying at him, how much energy has Jedediah gained? You'd gain it all. The kinetic would hit you in the face. The potential has gone down to give you the kinetic, and now you have calories. The cheeseburger launched at Jedediah from on top of the school. A scenario you probably will never see. So let me do an example of this. In an ideal situation, no situation is ideal, but in an ideal situation, we're going to talk about 100% energy efficiency. What that means is all potential energy is going to be converted into kinetic energy as the object falls. Is this realistic? Jedediah says no. Jedediah, you are correct. This is not realistic. Why not? What do falling objects realistic? What do falling objects do as they speed up? They also, no, as they speed up, they also gain what? Thermal energy. They get hotter. Objects that fall in the presence of air are going to heat up due to the friction of the air. So what we're doing here, this is not realistic because of the air. We're going to ignore the air. We're going to pretend it's not there. Ignoring the air, we're going to drop a cheeseburger on Jedediah. How fast does the cheeseburger hit Jedediah? There we go. It's a house for ants. Bonus points if you get the reference. Nobody gets the reference? It's probably good that you've not got the reference. No, it's a Ben Stiller movie. What is this? A School for Ants? With Owen Wilson? Ben Stiller, Owen Wilson, Will Ferrell? No? Zoolander. Anyway, totally unrelated. Let's do this. We've got a ball. Forget the ball. We got a cheeseburger. And Jedediah is lying on the ground. We are going to drop a cheeseburger on Jedediah's face. You're never getting away from the cheeseburger, Jedediah.
Yeah.
The cheeseburger, it's a 2-kilogram cheeseburger, which is a 4-pound cheeseburger. That's a big, big cheeseburger. We got a 2-kilogram cheeseburger being dropped on Jedediah from a height of 10 meters. 10 meters is 36 feet. 36 feet is like 4 stories. So one more classroom on top of this, and we're dropping the cheeseburger out the window on Jedediah as he lies on the ground waiting for the cheeseburger. How much is this going to suck? Well, let's look at what happens here. At the beginning, if physics is all, I like physics, it's all about the numbers, but the language is so important. If we're dropping the cheeseburger, what is the implication of the word dropped? You're just letting it go. If you just let an object go, does it have any initial velocity? If I'm holding an object here, it has nothing to start, and I let it go and gravity takes over. So we're dropping the cheeseburger on Jedediah. We're not throwing the cheeseburger down on Jedediah. Okay? That's an important distinction. Up at the top here, we're going to have potential energy, but no kinetic energy. No EK. Because the object is not moving at the beginning. At the end, is it going to have any potential energy? When it impacts with Jedediah on the ground, will it have potential energy? Well, will it? Potential energy is measured as the height above something. If the cheeseburger's on Jedediah on the ground, is it above anything? No. No, it's impacted his face. The cheeseburger is now all over Jedediah. So at the bottom, potential energy is going to equal 0, and kinetic energy is going to equal its maximum possible value. At the top, you're going to have max PE. At the bottom, you're going to have max EK. So this is fun. What is the potential energy of the cheeseburger to start? That's not going to happen.
No.
That is absolutely not going to happen. How much potential energy does the cheeseburger have to start? Well, PEG equals, because it's asking for potential energy, mgh. We know the mass of the cheeseburger is 2. The gravity, because we're on Earth, is 9.81. And the what? Height is 10. Take those values, we're going to plug them in. 2 times 9.81 times 10 is going to equal 196-ish. 196.2? Not a very scary number, given that we've had some much larger numbers. But if we're assuming 100% efficiency, this thing is not heating up, what is the kinetic energy of the cheeseburger on the ground? As it impacts the ground, what's the kinetic energy going to be? There's no math here. Look at what's happening. This is one of these scenarios. At the beginning, we have no kinetic energy. At the end, we have no potential energy. So all of your potential energy is going to become kinetic energy. So how much kinetic energy does the cheeseburger have as it hits Jedediah? It's not a trick question. How much energy did it start with? How much energy does it have to have at the end? 196. It's got to be the same. The energy is not going anywhere. It's just getting transformed from potential to kinetic. But it still has to have that same value. So the kinetic energy, EK, whatever, how did I write it? EK is going to have to equal 196.2 joules. It doesn't go anywhere because we're ignoring the air. So now the question is, how fast is this cheeseburger going when it hits Jedediah in the face? Here we go. And can he eat it fast enough so that it's, he just eats it as it comes down? Probably not. Here we go. We want to find out what is the velocity of the ball when it hits the ground. And it starts with given the kinetic energy. So this is a EK equals half mv squared kind of situation. We know that the cheeseburger has a mass of 2. It has an energy. We know the EK is 196.2. So now we're going to plug it in and solve. 196.2 goes in for EK is going to equal half times 2 times v squared. These numbers are nice. What's the first thing we can do as we solve this problem? To make our life a little bit easier. Half of 2, which is 1. That's just going to give us 196.2 is equal to 1 v squared. We don't have to write the 1 if there's a 1 there because multiplying by 1 doesn't change anything. So now to find v, what do we have to do? Square root. How fast is the cheeseburger going when it hits Jedediah in the face? What is the square root of 196.2? You should know this, actually. I made my grade 9s memorize this. What is the square root of 196? That is a perfect square. Kohi is 14. Any one of you who had me for math 8 or math 9? Should have that locked in. But if you've forgotten, you'll get a calculator. So, perspective. What is 14 meters per second? That cheeseburger is moving at 50 kilometers per hour. Just to put that into perspective, that is a cheeseburger moving at 50 kilometers per hour. It's not going to kill Jedediah, but that's not going to be a comfortable experience. Especially since this isn't your typical McDonald's cheeseburger. This is a bag full of 8 quarter-pounders. No, it's more than that. 2 times 2.2 is 4.4. That's 4.4 pounds. No. No, divided by 0.25. That's 18 quarter-pound cheeseburgers hitting you in the face. I converted it for you to give you perspective. If you recall, this. Going from meters per second back into kilometers per hour, you multiply by 3.6. You do it the other way. Okay. So that is the last. You have 25 minutes. Here is your homework. I'm going to flip the page. There are a bunch of questions. 7 questions. I would like you to do these 7 questions. I'm just going to throw some numbers. I want you to write down the following numbers. Just up here at the top of the page for me. 450. 4. 6. 45.9. 205,800. 55,125. 49.5. 1.02. 4.47. You're writing down some numbers. 76.7 and 220,500. Those are the answers to the questions you're about to do in no particular order. There you go. You have your task and you have the answers. You just don't know which numbers go with which questions. On your mark, it's set, giver.